Hello again and welcome back to Chemistry. It is all that matters, and today we're going to look at another way of arranging our electrons, and we're going to do that through a process called orbital notation. Now we are reminded from the previous arrangement of electrons using electron notation and electron configuration that there are 7 levels to our periodic table, and there are basically 4 blocks of orbitals, and in the orbitals there are suborbitals. So we have the 7 levels of the s orbitals, then we have the 2 through 7 p orbitals, and inside the p orbitals there are 3 suborbitals. Then we have the 4 levels of d orbitals, and inside the d orbitals there are 5 suborbitals. And then you have the 2 levels of the f orbitals, and those include 7 suborbitals. So let's look at how we do orbital notation. So let's start with an element like lithium. Now in lithium has an electron configuration of 1s2, 2s1. It has 3 electrons. So the first electron we know goes in the 1s orbital, so we're going to pull an electron into the 1s orbital. And there's a pair to that, so that is the second electron. And we always have one arrow going up and one arrow going down because the electrons have a positive and a negative spin. And the first electron is always the positive spin heading up, and the second electron is the negative spin going down. And I guess the best way to think of this is electrons are both negative, so they're going to repel each other, so they're going to be moving in opposite directions away from each other. So that's why a good way to recognize this or to notate this would be to use the electrons as heading in opposite directions, one positive, one negative. Now the 2s orbital would hold 1 electron, so we bring 1 electron there. And these 2 boxes, or blocks, or orbitals, or suborbitals, however you want to look at them, would represent the electron orbital notation for lithium. So let's go ahead and try another one. Let's do oxygen. Now oxygen is 1s2, 2s2, 2p4. So we know the 1s2, that orbital, is going to hold 2 electrons. And we know that one is going to have an upward spin, one is going to have a downward spin, or a positive spin and a negative spin. The 2s orbital likewise is the same. So we have 2 electrons, one with a positive spin, one with a negative spin. And then when we get to the 2p orbital, when we fill the p, we always fill the up orbitals first, or up electrons first. So the positive electron spins always go first, and you must fill each suborbital with a positive spin electron before you pair. So in order to get 4 electrons, there are going to be 3 up electrons in each of the suborbitals, and then you will pair the 4th electron in the first suborbital. So here we have 2 electrons in the 1s, 2 electrons in the 2s, and 4 electrons in the 2p. So this is the orbital notation for oxygen. As we move out to aluminum, aluminum has 13 electrons, 1s2, 2s2, 2p6, 3s2, 3p1. Now, we know the 1s has 2 electrons, 1 up electron, 1 down electron, or 1 positive spin, 1 negative spin. The 2s orbital has 2 electrons, 1 positive spin, 1 negative spin. When we fill the 2p, remember again, we are dealing with filling each of the suborbitals with their positive electron first before we pair. Now, in the 2p, we see that it's 2p6, so we know that there's going to be a full orbital, so each of the suborbitals would have to have a positive spin and a negative spin electron, making the total of 6 electrons in the 3 suborbitals. And then when we go out to the 3s, we have 3s The first electron is an up spin, the second electron is a down spin, or a positive spin and a negative spin, and then in 3p we have one electron in the 3p. So there are 13 electrons, 1s2, 2s2, 2p6, 3s2, and 3p1. Let's do one last example, and here we have arsenic. Arsenic is Ar for argon, 4s2, 3d10, 3p3. Now we know the arsenic is telling us that levels 1, 2, and 3 are all full. So I'm not going to fill those. I'm just going to go to the 4s level and we'll look at those electrons. So we're going to have 4s2 has 2 electrons, a positive spin and a negative spin. We know the 3p is going to have a positive spin, a positive spin, and a positive spin, making it 3p3. And the 3d10, that tells us that each of the d suborbitals is filled. And that gives us our 10 electrons in the d orbitals. And we know that each of the suborbitals below that would all be filled because that would be what is represented by the argon for the core notation in the electron configuration for arsenic. So arsenic would end as 4s2, 3d10, 3p3. Now there are 3 basic rules to the orbital notation. The first rule is called the Aufbau Principle, and the Aufbau Principle says that you have to fill the first level before you fill the second level. So you can't fill a higher energy level until the lower energy level below it has a complete suborbital set. So the second rule is called Hund's rule, and Hund's rule says each suborbital must have an electron in it before you fill the rest of the suborbitals. So you can't put 2 electrons in the first p suborbital until each of the 3 suborbitals have 1 electron. And the third rule is the Pauli Principle, which says that no 2 electrons may occupy the same energy, and that's why we have an up electron and a down electron, or a positive spin electron and a negative spin electron, because they must spin in opposite directions in order to have different energy. So let's look at a couple of cases where these rules are being broken. So which rule is being broken here? So take a moment, think of the 3 principles I just went over, and decide which one is being broken here. Hopefully you said the Aufbau Principle. And why the Aufbau Principle is being broken here is the lower energy level has not been filled, and we're already filling an upper energy level. So this is the Aufbau Principle. You must fill the lower energy levels before you move to the next energy level. So let's look at the second one. So which orbital notation rule is being broken here? Okay, this is Hund's rule, and Hund's rule says that you must have an electron in each suborbital before you pair them up. So having a pair in this second suborbital is not allowed unless we have an electron in this far right suborbital. So let's look at a third way that the orbital notation rules can be broken. So which rule is being broken here? And this, of course, is the Pauli Principle. And this middle suborbital, we have 2 up electrons, or 2 positive spin electrons, they would be sitting in the same energy level, so therefore that is breaking the Pauli's principle. This electron actually needs to be flipped in order to be correct. So which rule are we breaking here? This, of course, is Hund's rule. We need to move this electron over to this suborbital and flip, because you have to have the positive spin before you have the negative spin. So now we have a corrected version. And one more example. So what seems to be the problem here? Which orbital notation rule is being broken here? Now, actually, we're going to have two rules broken. Now first we have to bring these electrons down to the lower sublevel, the lower energy level, because we have to follow the Aufbau Principle. And then in order to make sure we're not breaking the Pauli Principle, this electron needs to be moved over to this suborbital and has to be a positive spin. So now we have a correct version of that electron configuration. So this is how you do orbital configurations, and primarily we're going to use orbital configurations when we're talking about what are called valence electrons, so we would only be looking at the highest energy level electrons when we do an orbital notation. And we'll continue to practice this throughout the semester. So keep working on your chemistry.